Bismillah ar-Rahman ar-Rahim. Let's continue where we left off last time. So last time we were looking at how to add vectors. So when we have two or more vectors, how do we add them to give us the resultant vector? So now we are asking the other question, that given any vector v, how can we write it as a sum of two vectors? Okay, so this is what we call the resolution of a vector. So we want to resolve this vector as sum of two vectors. Okay. In the most commonly used case is when we want to resolve the vector into perpendicular components. Okay, what do I mean by that? So I want to resolve v such that its components are perpendicular to each other. So let me just write it out for you. So we want to write v vector as some vector vx plus some other vector vy such that the condition is that vx dotted with vy is equal to 0. And as you might have already known before this course also, that if two vectors have a dot product equal to 0, we know that these two vectors are perpendicular. Okay, so we want to write this vector v as its perpendicular components. Okay, this is what we call perpendicular basis. And writing this vector to resolve a vector into perpendicular components, first we have to choose the basis. So let's just reiterate. First choose a basis, or we can say choose an axis. Okay, so once we have chosen an axis, then we can write this vector into its components. So for example, here we have chosen this x and y axis, so I can now write v as its two components. This component is in this x direction and this component is in this y direction. Okay, and if we want to find the magnitude, we can use the sine and cosine identities to find the magnitudes. What do I mean by that? So I know that cos of theta is going to be equal to Vx magnitude divided by V magnitude. Again, why these are not the vectors anymore? These are the magnitudes of that vector. So you might have already seen this convention. When we put these two straight lines around a vector, that means we are talking about the magnitude of that vector. So the length, because this forms a right angle triangle, and we know that cos of theta is equal to base over hypotenuse. In this case, base is equal to the magnitude of Vx and hypotenuse is the magnitude of total vector V. Similarly, we can also say that sine of theta is going to be equal to magnitude of Vx, Vy, divided by V. So you can already see that it's not very difficult to resolve a vector into its components if you know the direction of and the length of the original vector. So to find Vx, we can just say that Vx is equal to the magnitude of Vx is equal to magnitude of V times cos of theta, and the magnitude of Vy is equal to magnitude of V times sine of theta. So it's pretty straightforward in the sense that you do not need there is no ambiguity. We can do it for any number of vectors. So for example, in this case, this vector is vector A and this is vector B. So this red line is the x component of vector A, and this red vector is the y component of vector A. And this other vector B, this is the blue component, is the x component of vector B, and this blue component is the y component of vector B. So any number of vectors we have, we can just resolve them into their perpendicular components. Okay. So let's move on. So now there are some rules about resolution of a vector in terms of in which plane it would be, which quadrant I should say. You would have already studied this part also, so let me just reiterate it for you. So let's assume that we have something like this. So this is my x-axis and this is my y-axis. So I know in this part of this graph, I have x is positive and y is also positive. Okay. However, in this part of the graph, x is negative but y is positive. Here both of them are negative, and here y is negative but x is positive. So what I mean here is that this is the x and this is the y, and similarly for all of them. Okay. So why does it matter? Why are we worried that which component is positive and which is negative? So I know that when I am computing sines and cosines, I have to be careful, because let's just say that if sine of theta is equal to 2 over 3, but that is also equal to minus 2 over minus 3. So whenever we are using trigonometry to find angles, so there is some ambiguity. So in this case both of them are negative, but we still get the same angle theta. Okay. So we have to be careful if by looking at the numbers, if one of them is negative, then we have to see which quadrant it is going to be in. Okay. If both of them are negative, if x component and y if the angle from this side is greater than 180 or it is greater than pi, so it's something here. So we already know that sine of this property of sine, that sine of theta is equal to first of all it is equal to minus sine of minus theta. So, and we have many more properties of this, and these properties relate to these quadrants. Okay, so we have to be careful that if both x and y components are negative, then we are in the third quadrant. Okay, so this is what we call the, let me just write it with the, so this is called the first quadrant. This one here is known as the second quadrant. This one here is known as the third quadrant, and this one here is the fourth quadrant. So it becomes really tricky when we are making tangents. Okay, so so let me explain this concept a little more by using an example. So I hope this part is clear. So let me just get rid of this and try to explain using an example. So let's assume that we have these axes, x and y, and we have a vector here, and the components of this vector, so let's just say this is -3 and this component is -2. Okay, sorry, 2. So now this vector, I want to find this angle. So this angle is theta, angle from the x-axis. Okay, so the first thing to understand is that using the formulas that we discussed last time in the previous slide, we can say that theta is equal to tangent inverse of the x component of a vector. So I just call it vy, magnitude of vy divided by the magnitude of vx. So now in this case, vy is equal to 2 and vx is equal to 3. So this is equal to tangent inverse of 2 by 3. So here we are. So there are a few points that I want to make here. So even if this vector were in the first quadrant or the second quadrant or the third or the fourth, this theta would come out to be 2 by 3. Okay, why it would be 2 by 3? Because magnitudes do not care about sign. Okay, so the magnitude is still going to be 2, the magnitude is still going to be 3. So even if so the real tricky situation is when we are dealing with first and the third quadrant. So this is the first, oh sorry, I think this is not very easily visible. So this is the first quadrant and this is the third quadrant. So we know that 2 by 3 is the same as writing -2 divided by -3. So using tangent inverse, we would not know which quadrant our vector is it in, but we have to be careful by looking at if my y component is in the negative direction and x component is in the positive direction. So I have to see y in negative and x is positive, means that this vector is in the fourth quadrant. Okay, if both of them are negative, I know that this is third quadrant. If x is negative and y is positive, this is the second quadrant. If both of x and y are positive, we know that this is first quadrant. So this is what I am trying to explain here, that if y component and x component are positive, when we find the theta, this is going to be just this simple angle. If x is negative and y is still positive, we will find this angle. Okay, so if both of them are negative, then we have to find this angle. Okay, this extra angle, and when x is positive and y is negative, we can find this angle, but this would be in the clockwise direction. Okay, So these things will get more clear as we move on, inshallah. So the take home lesson from this is that you cannot just use tangent inverse without looking at the signs of your components, because then you won't know that which quadrant that vector is in. Okay, so I hope everybody got this message loud and clear. Let's continue with our discussion of resolution of a vector. So we have already seen how we can resolve a vector so into its components into perpendicular basis. Okay, but now we want to look at how we can resolve vectors into non-orthogonal or non-perpendicular basis. Okay, so now the problem is what happens when we have two vectors which are not orthogonal to each other and we want to resolve a vector into its components. So for example, we have this vector f and we want to resolve this vector f1 into u vector and v vector, and where the angle between u and v vector is not 90 degrees. Okay, so to explain this point, so let me just clarify the picture for you. So we have the u vector pointing in this direction and then the v vector pointing in this direction, and now the angle between the two is 70 degrees. It is mentioned as it is mentioned here. Okay, so now when I want to resolve this vector into its components, so the first vector is going to be like this and the second one is going to be like this, and this angle is 70 degrees. Okay, so now we would have to use some trigonometry, because this angle we already know is 30 degrees. And because the remaining angle, we can do the calculation, this angle is going to be 40 degrees. And because these two lines are parallel to each other, so we know that, and these two lines are also parallel, so this angle is also going to be 40 degrees. Okay, and so the remaining angle, because all the sum of the three angles of a triangle is 180 degrees, so I can say that this angle is equal to 110 degrees. Okay, so I can solve this. What do I want to find? I want to find the length of u and the length of v vector such that their sum is equal to f1. So the question is I want u plus v to be equal to f1. What u and v can I choose so that their sum equals f1? The simple answer is that we can just use sine rule. So I know that sine of 40 divided by the magnitude of u. Notice when I do not put an arrow on the top, that means the magnitude. So I can just write it like this. So let me just clarify. Magnitude of a vector is equal to just the vector without any arrow on the top. Okay, this is just convention. So this is equal to, so this angle is 110, sine of 110 divided by this length f1, which is 300. Okay, from here we can find the magnitude of u. Similarly, we can do the similar thing for for V, and you can find the magnitude of V. So this I found a really good video online, so you guys can go ahead and watch this video.
In this video, I'll show you an example of resolving a force, or any vector for that matter, into components acting along directions that are not at 90 degrees to each other. In this particular problem, we're just going to look at the force F1, which is 300 newtons and acts at 30 degrees to this u-axis. Okay, so we want to know the components of this force F1 along that u-axis and also along the v-axis. So we'll start our solution by drawing our vector force F1. Then we'll draw our required axes u and v. And we recall that finding the components of a vector is kind of like the parallelogram law of addition in reverse. So we'll draw lines at the tip of F1 parallel to our axes. So here we've got a line parallel to the axis u at the tip of F1, and then we have another line here parallel to the axis v, also at the tip of F1. So we know that the components of a force must add up vectorially to give us the original force. So we would have component acting along here u direction plus a force component acting along the v direction here to add up to give us F1. We could also consider a force here along the v direction, so the force component v plus the force component u. So let's draw those in. So we have the component Fu and the component Fv acting along those directions. Okay, so let's label those. F1u and F1v. So now, having drawn our vector diagram, we just need to make use of trigonometry. So we'll work out, or we can see that this angle here is 40 degrees, because we've got a total of 70 here opposite our 70 over here. So we can put that on our vector diagram. And then from alternate angles, we can see that this force here will also be 40 degrees. Okay, so this angle here is the alternate angle to this one. And from our information given, we know this angle is 30 degrees. And from the sum of the internal angles of a triangle adding up to 180, we can see that this angle in here is 110 degrees. So what we're trying to do here is to work out the length of F1u and also the length of F1v. And we know the length of F1 because that was given in the problem, and we've now worked out all the angles. So if we know angles and a side, and we have two unknown sides, then we can just use the sine rule twice to solve for those unknown forces. So first, let's look at F1u. So we have here F1u, the opposite angle is 40 degrees. So we have F1u over sine 40, and we know the length of F1, and the opposite angle there is 110. So we've substituted that into the sine rule, and we can now rearrange that equation to solve for F1u, which comes out at 205 newtons. Okay, so let's do the same thing for F1v. So here, F1v, its opposite angle is 30 degrees, so it will be F1v over sine 30, and we can just use the same ratio from the previous example. So F1 over sine 110. Let's do the calculations. Rearrange that equation to solve for F1v, and we get 160 newtons. So now let's summarize our answers and write at the end that our final answers are the component of F1 in the U direction is 205 newtons, and the component of F1 in the V direction is 160 newtons. And remember that components do not have to be at 90 degrees, although most often that's what we do calculate, but in this case our components are not at 90 degrees to each other. And as you've seen in this problem, knowing all of your angle relations, trigonometry and geometry that you should have learnt in high school is very important for solving these engineering mechanics problems. And you thought all that stuff that you learned in high school was useless, didn't you?
So now we continue our discussion and we look at addition of coplanar vectors. Okay. So there are two things that you have to understand. Whenever we are talking about vectors, sometimes we represent vectors in this scalar notation, and there are two very common notations that are used. First notation is the angle and magnitude notation. So when we have a two-dimensional vector, we can represent it using its x component and y component, but we can also represent the same vector by giving the magnitude of that vector and giving the angle relative to some axes. Okay, so for example here I could tell you the value of fy and fx, and that would completely specify this vector f, but I could also tell you the magnitude of f, and I could tell you the angle that this vector makes with the horizontal axis, and it would still completely classify the same vector. And so in this case, of course both of these are interchangeable. So given f and theta, I can always find fx and fy, because from this we understand that using trigonometry, fx is just f cos of theta and fy is just f sin of theta. So the two are interchangeable. The second way we use 2D scalar notation is by giving these ratios of angles. Okay, so for example here on this vector f, we are given this smaller triangle with sides A, B and C. What does that mean? That this triangle is similar to this bigger triangle. So that means that the ratios are the same, which means that, let me just write it down for you. What does that mean? So as here we can see that this C is same as f and A is same as f of x in terms of ratios. So we can say that f of x divided by f is the same as A divided by C, and similarly we can say that fy divided by f is same as B divided by C because of similar triangles. And from these we can see that f of x is equal to f times A divided by C, which is what we have here, and fy is just f times B divided by C, which is what we have here. And so in this notation we have to be careful about the negative sign, because here we already see that fy is in negative direction. So we know that minus fy over f should be equal to this, which gives us that fy is equal to minus f times B over C. Okay, so we put the negative and positive sign depending on which quadrant we are dealing with. Okay, so it's I hope this part is clear. So these two are notations which are very commonly used in coplanar forces. So this is only more appropriately used in coplanar forces when we are looking at a 2D system. So by coplanar we really mean a 2D system. Okay, so that all the forces lie in a plane. So there is nothing which if this surface of the screen is our plane, there is nothing which lies outside of this screen. Okay, so I hope this point is clear. So now we look at addition of coplanar vectors. So for example, we have this vector f. We can write this vector into its x and y components. So we choose a unit vector in x direction and we call it I vector. Sometimes it is also called I hat. So this vector I is sometimes also known as I hat, and this is basically the unit vector in x direction. And the second vector is the j vector, also sometimes referred to as j hat, which is the unit vector in y direction. Okay, so we can write this vector f as fx times I hat plus fy times j hat vector. So we can, this is what we call the Cartesian vector notation, and we can use this Cartesian vector notation to add vectors. Okay, so we can, so now that we have understood all the concepts related to coplanar forces and how to resolve them and how to find the resultant of a force, so now we look at some examples. Okay, so this is an example from the book. It is fundamental problem 2-7. So the problem says resolve each force acting on the post into its x and y components. Okay, so we have three forces acting on this post. This is force F1, which is 300 newtons pointing towards the y axis. F2 is 450 newtons pointing 45 degrees to the minus x axis, and F3 is 600 newtons pointing in this direction. Okay, and we want to resolve all three forces into their x and y components. Okay, so let's begin by one. So first of all, we can resolve the F1. So F1 I know is, so F1 I know that is, it is completely in the y direction, in positive y direction. It does not have any component in the x direction. So I can just say that this is equal to 300 j hat, and you can put Newton if you like. So let me just put a Newton here. Okay, so so you understand that because it was vertical, this force is applied vertically, so it did not have any x components at all. So this was pretty straightforward. So now we look at F2. So F2 is applied at 45 degrees to the negative x axis. So I can say that F2, so first of all we know that the x component of F2 is going to be in negative direction because it is in the negative x axis. So we put a negative sign, and 450 times sine of 45 degrees, or actually this has to be a cos, but because the angle is 45, it doesn't matter. So let's just make it clear as we can. So this is cos of 45 degrees. So this component is in I hat direction, and plus 450 times sine of 45 degrees j hat component. And we know that cos of 45 is equal to sine of 45, which is just equal to 1 over square root of 2. Okay, and which turns out to be 0.707 or something. Okay, so I'm pretty sure you can do the math here, but my point was to tell you that how these components are supposed to be written. Okay, so now we look at F3. So F3, again for F3, both the x and y components are going to be positive. So this is F3. So this is F3, and the x component has a ratio of 3 by 5, and y component has a ratio of 4 by 5. So I can say that 600 times 3 by 5 I hat is the x component, again because it has an I hat, so this means this is an x component, and 600 times 4 by 5 is the j hat component. And we can simplify this. 600 divided by 5 is equal to 120. 120 times 3 is 360. So this is 360 I hat, and it is also given in newtons, plus 120 times 4 is 480. Newtons in the j hat component, j hat direction. Okay. So this is how we resolve all of these three forces into their x and y components. Okay, so this, we have solved this first problem. Let's move to the next one. And so this problem says that determine the magnitude and direction of the resultant force. Okay, so we have a hook here. It has three forces acting on it. So this is a 250 Newton force acting in this direction, 400 Newton force acting on this direction, 300 Newton force acting in this direction. So even though these three forces are not acting at the same point, but because they are acting in a direction which leads to the same point, so we can assume this to be a particle. Okay, and so we can assume that all the three forces are acting at one point, and this is this hook is just a point particle. Okay, and we want to find the resultant of the three forces. Okay, so first of all I will try to break these forces into their x and y components. So this force I can write it as 250 times 4/5 j hat I hat, sorry, 4/5 has to be I hat, plus 250 times 3/5 j hat. Okay, so this is the resolution of this force into its x and y components. Okay, similarly this force can just be written as 300 I hat, but this third force, this has to be written as 400 cos of 30 degrees I hat, plus, again, so we made a mistake here that one of the components had to be negative because it was in negative direction, so this other component had to be in negative direction, and this component, both of these components have to be positive, so I say 400 sine of 30 degrees. Okay, so now that I have written all of these three forces into their x and y components, I can just say that the resultant force is nothing. So I just add the x components. So x components are 300 plus 400 cos of 30 minus 250 times 4 over 5, and all of this with I hat. Okay, and plus, so for the j hat component, this does not have any j hat component, so I have 400 sine of 30, so this has to be a degrees here, plus 250 times 3 by 4, and all of them j hat component. So we can write it into I hat component and j hat components. Okay, so I hope this is clear.